morning began in silence. Not the absence of sound, but the quiet certainty of a world behaving exactly as it should. On September 1st, 1859, the sky above southern England was clear, pale, and unremarkable. The sun rose as it always had, unchallenged, constant, indifferent to the fragile routines unfolding beneath it. In a private observatory just outside London, an amateur astronomer named Richard Carrington climbed a narrow staircase and stepped beneath the curved dome of his instrument room. It was a ritual he had performed countless times. He opened the shutter, aligned his brass telescope, and projected the sun's image onto a flat screen. There, he began to sketch. The surface of the sun was not smooth. It was marked, freckled with dark regions known as sunspots. Carrington had been tracking them carefully, noting their size, their movement, their slow drift across the solar face. These spots, some larger than the Earth itself, were already understood to be unusual. But they were not alarming, not yet. At approximately 11:18 in the morning, something changed. Carrington would later describe it with measured restraint, but even his words strained against what he witnessed. From within the cluster of sunspots, he saw what he called two patches of intensely bright and white light. They appeared suddenly, violently, like wounds opening in the surface of the sun itself. The brightness was so extreme it rivaled the surrounding solar disk, something no ordinary feature could achieve. He watched, stunned. For 5 minutes, the light burned. Then, just as abruptly as it had appeared, it vanished. Carrington initially suspected an optical illusion, a flaw in the instrument, a trick of the eye. But another observer miles away reported the same phenomenon at nearly the same time. What they had seen was real. It was unprecedented, and at that moment it was not understood. What Carrington had unknowingly recorded was the first observed solar flare in human history. The energy released in that brief flash has since been estimated to equal billions of megatons of TNT. An eruption of magnetic energy so vast it defies ordinary comparison. But the light itself was only a signal, a warning. The true event had already begun. Beyond the visible flash, the sun had expelled something far more dangerous. A vast cloud of charged particles in magnetized plasma hurled outward into space at extraordinary speed. Traveling at over 2 million kilometers per hour, it crossed the 150 million kilometers between the sun and Earth in less than 18 hours. Normally, such a journey takes days. This one did not. At the time, no one on Earth knew it was coming. There were no satellites watching the sun. No instruments positioned between worlds to detect the invisible surge. The sky remained calm, the air unchanged. The routines of daily life continued without interruption. And yet, beneath that calm, the planet was already beginning to react. The Earth is not an isolated body. It is wrapped in an invisible structure, a magnetic field generated deep within its core. This field extends far into space, forming a protective boundary known as the Magnetosphere. It deflects charged particles, shields the atmosphere, and preserves the delicate balance required for life. But it is not immovable. When the solar storm arrived, it did not strike the ground like an object. It struck the field. The magnetosphere compressed, distorted, and began to vibrate under the impact of the incoming plasma. Magnetic field lines twisted and reconnected. Energy poured into the system. And as it did, something subtle and deeply consequential began to occur. Electric currents were induced, not in one place but across the entire planet. The Earth itself began to behave like a conductor. At first, there was no panic, no immediate recognition of danger. But within hours of Carrington's observations, small anomalies began to appear. Instruments designed to measure magnetism behaved erratically. Needles drifted, then snapped off scale entirely. Observers noted disturbances but had no framework to interpret them. Then, as night approached, the sky changed. Far from the polar regions where such phenomena belonged, strange lights began to emerge. Curtains of red and green spread across the horizon. In places as far south as the Caribbean, the darkness dissolved into shifting color. The intensity was unlike anything recorded before. The sky did not merely glow, it burned. In some regions, the light was bright enough to cast shadows, bright enough to read by, bright enough to confuse the boundary between night and day. People stepped outside, uncertain of what they were witnessing. Some believed distant cities were on fire. Others feared something more final. The atmosphere itself seemed to have transformed into something alive, something unpredictable. And still the full extent of the disturbance had not yet revealed itself. Across continents, thin copper wires stretched between cities and towns. These were the arteries of a new kind of civilization. Telegraph lines carrying messages at the speed of electricity. They were the most advanced communication system humanity had ever built. Within hours, they would become something else entirely because the currents now flowing through the earth were not contained. They sought pathways, and in those long metal lines they found them. What Carrington saw lasted 5 minutes. But what it set in motion was already unfolding across the entire planet, silent, invisible, and unstoppable. And by the time humanity began to understand what was happening, it was already too late to stop it. Ready for this journey? Well, subscribe to our channel to get more content like this. By the time darkness settled across the continents, the disturbance had found its way into the veins of human civilization. The telegraph network, thin strands of copper stretched over thousands of kilometers, was never designed to carry anything more than controlled pulses of current, measured signals, intentional messages. It was a system built on precision, on predictability, on the assumption that electricity would behave. That assumption began to fail. Operators across North America and Europe were among the first to notice it. At first, the anomalies were subtle, faint fluctuations in current, irregular clicks in the sounders. Then, without warning, the system surged. In Pittsburgh, telegraph manager E.W. Colgan observed something deeply unsettling. The currents flowing through his lines were no longer stable. They rose unpredictably, intensifying beyond anything the equipment was built to handle. Platinum contacts, chosen specifically for their resistance to heat, began to glow. There were reports that they came dangerously close to melting. Then came the fire. Colgan described streams of fire pouring from the circuits as though the wires themselves had been ignited from within. This was not a localized malfunction. It was not the result of a faulty battery or damaged line. It was something else, something feeding energy into the system from outside. Across the network, similar reports began to emerge. In Washington, D.C., telegraph operator Frederick W. Royce was working at his station when the surge struck with violent force. As he leaned forward, his forehead briefly touched a grounded wire. In that instant, a powerful electrical shock coursed through his body. Witnesses later described a visible arc, a flash of energy. Jumping from his head to the equipment, the system was no longer safe to touch. Operators instinctively pulled back, some abandoning their posts entirely. Others attempted to continue working, driven by the urgency of maintaining communication. But the machines had become unpredictable. Sparks leapt from metal components. Paper used to record messages began to scorch and ignite. In stations that relied on chemically treated paper, the heat from the surges was enough to set it alight. It was as if the network itself had come alive. And yet, in the midst of this chaos, something even more extraordinary began to happen. In multiple locations, operators made a discovery that defied everything they understood about electricity. They disconnected their batteries. Under normal conditions, this would render the system inert. Without a power source, no signal could be transmitted. the circuit would be dead. But on that night, the circuits were anything but dead. Even with the batteries removed, the telegraph lines continued to carry current. Messages could still be sent, unevenly, unpredictably, but undeniably. In Boston, operators found that they could transmit signals to Portland, Maine, at intervals ranging from 30 to 90 seconds. The timing was erratic, the clarity inconsistent, but the connection existed. The system was powering itself, or rather it was being powered by something else. For the first time, the operators were no longer in control of the current flowing through their wires. They had become observers, watching as an unseen force took command of their machines. The infrastructure they had built to transmit human thought was now acting as a conduit for something planetary in scale. The realization came slowly and without the language to fully articulate it. The Earth itself was conducting electricity. Beneath the surface, currents were moving, vast, diffuse, and powerful. The magnetic disturbance triggered by the solar storm had induced electrical flow within the ground, within the oceans, within the very structure of the planet. And those currents were finding paths of least resistance. Long metal wires stretched across continents provided exactly that. What had been designed as a communication system had become an extension of a much larger circuit. The implications were staggering, though not yet fully understood. The telegraph network spanned thousands of kilometers, connecting cities, economies, governments. It was, in many ways, the first global technological system. And now it was being overwhelmed, not by human error, but by a force originating 150 million kilometers away. In station after station, operators reported the same phenomena: uncontrolled surges, sparks erupting from instruments, shocks delivered through equipment, and currents flowing where no current should exist. The scale of the disturbance was becoming impossible to ignore. This was not a localized storm. It was not confined to a region or a single line. It was global. Everywhere the wires stretched, the effect followed. Some operators attempted to adapt. By carefully adjusting their equipment, timing their transmissions to the irregular pulses of current, they found ways to continue sending messages. It was crude, unreliable, but functional. For brief moments, human communication persisted, piggybacking on a current that did not belong to them. But even these efforts revealed something deeper. The intervals between usable signals were not random. They followed patterns, bursts of activity followed by silence, then sudden surges again. It was as though the entire system was breathing, expanding and contracting under the influence of an external rhythm. A rhythm that no one on Earth could control. Outside, the sky continued to burn with unnatural light. Inside, the wires carried currents that no battery had produced. The boundary between the natural world and human technology had dissolved. The distinction between Earth and machine was becoming unclear. And still, the question remained unanswered. What could drive such immense currents through the ground itself? What force could reach across space, strike an invisible magnetic shield, and transform an entire planet into part of its circuit? The answer was already there, written in the brief flash Carrington had seen that morning, encoded in the particles now colliding with Earth's magnetic field. But in that moment, for those standing beside sparking wires and burning paper, it was something far more immediate, something they could feel. Because if the ground beneath their feet could carry current, then whatever was driving it was not just above them. It was already here. Night arrived, but it did not bring darkness. Across vast stretches of the planet, from the northern latitudes to regions that had never witnessed such phenomena, the sky began to change. At first, it was a faint glow along the horizon, subtle, almost easy to dismiss. But within minutes, the glow intensified, rising upward, spreading outward until the heavens themselves seemed to ignite. In places where the aurora had never been seen, across the Caribbean, over Cuba, above the islands of Jamaica, the sky transformed into something unrecognizable. Curtains of light unfurled in silence, shifting in color and form. Red dominated the horizon, deep and unnatural, as though the atmosphere had been set ablaze. Above it, streaks of green and violet pulsed and rippled, moving with a strange, fluid intelligence. To those witnessing it, there was no context, no scientific framework, only the raw experience of a world behaving in ways it never had before. In South Carolina, observers stared eastward as the sky turned a vivid crimson. The glow was so intense that many believed a distant city was burning. Some described the light as resembling a sunrise, except it was midnight. The ocean reflected the color, turning its surface into a shifting mirror of red and gold. Shells scattered along the shoreline caught the light and shimmered like embers, as though the beach itself had been scattered with coals. It was not just the sky that had changed. It was time. In towns and cities across North America, people woke from sleep, convinced that morning had arrived. Laborers rose from their beds and began preparing for the day's work. In the Rocky Mountains, gold miners stepped outside their cabins and, seeing the bright glow illuminating the landscape, assumed dawn had broken behind a veil of cloud. Fires were lit, coffee was brewed, tools were gathered. Only gradually did the realization set in. The sun had not risen. The light was coming from somewhere else. In Boston, the streets filled with people who could not ignore what was happening above them. Some stood in silence, watching the shifting colors. Others spoke in hushed tones, trying to reconcile what they were seeing with what they knew. And a few, finding the light strong enough to read by, took advantage of it. Newspapers were unfolded. Words were traced by a glow that did not belong to the sun, nor to any flame. The boundary between night and day had been erased. Even the natural world responded. In Virginia, birds stirred from their sleep. Larks began to sing at 1 o'clock in the morning, their internal rhythms disrupted by a sky that told them dawn had come. Their songs, meant to greet the rising sun, now echoed under a canopy of shifting color and silent fire. The confusion was not limited to animals. In Abbeville, South Carolina, workers rose from their beds and began laying bricks in the early hours of the morning, believing the day had begun. It was only after some time, after the absence of a rising sun became impossible to ignore, that they stopped, looked at one another, and returned home. Reality itself had become unreliable. The sky, once a fixed and predictable backdrop, had turned into something dynamic, something active. It no longer simply framed the world below, it was interacting with it, influencing behavior, altering perception, reshaping the most basic human understanding of time. And the light itself, it was unlike anything previously recorded. Descriptions from the time speak of a sky that pulsed and shimmered, the colors shifting in waves. Red dominated the lower regions, a deep, almost blood-like hue that stretched across the horizon. Above it, bands of green and yellow flickered and danced, sometimes forming arcs, sometimes breaking apart into scattered streaks. The movement was constant, fluid, almost alive. In some places, the intensity reached levels that defied belief. Observers reported being able to read small print outdoors long after midnight. Shadows were cast on the ground, not by moonlight, but by the aurora itself. The landscape was illuminated in a way that felt both familiar and profoundly alien, as though the rules governing light had been quietly rewritten. And beneath it all, there was a sense, difficult to articulate but impossible to ignore, that this was not a local event. It was everywhere. Reports flowed in from Europe, from North America, from regions separated by oceans and continents. The same colors, the same brightness, the same confusion, the same quiet unease. This was not a storm in the traditional sense. There was no wind, no rain, no thunder. The air remained still, the ground unchanged, and yet something immense was happening. What the observers could not see was the invisible interaction unfolding far above them. Charged particles ejected from the sun with enormous velocity were colliding with Earth's magnetic field. That field, distorted and compressed, was channeling the particles toward the poles. But under the extreme conditions of this event, the effect spread far beyond its usual boundaries. The atmosphere itself had become a stage for energy transfer. Atoms of oxygen and nitrogen, excited by incoming particles, released photons as they returned to their ground states. The result was light, brilliant, shifting, and under these conditions, global. But this explanation, precise and grounded in physics, would come later. In that moment, there was only the experience, a sky that burned without heat, a night that refused to be dark. A world in which the most fundamental assumptions about time, about light, about the stability of the heavens no longer held. For centuries, humanity had looked upward and found constancy. The sun rose and set. The stars moved in predictable patterns. The sky, vast and distant, followed rules that could be trusted. Now, those rules appeared to be breaking. And as the auroras continued to ripple across the heavens, as the red glow spread and deepened, as the boundary between night and day dissolved completely, a quiet realization began to take hold. This was not an isolated phenomenon. It was part of something larger, something connected to the disturbances in the telegraph lines, to the currents flowing through the ground, to the flash that Carrington had witnessed hours earlier. The sky was no longer passive. It was not merely something to be observed. It was acting, interacting, reaching down and altering the world below in ways that were only beginning to be understood. And if the sky itself could behave like this, then what exactly was it connected to? What do you think about this question? Do share with us in the comments section and be ready to dive into some physics. Inside the telegraph offices, the world had become something unrecognizable. The instruments were still there, the keys, the wires, the relays, everything arranged exactly as it had been hours before. But the behavior of the system had changed so profoundly that it no longer felt like a machine under human control. It felt occupied. Operators sat at their stations, hands hovering uncertainly over equipment they no longer trusted. The sharp, rhythmic clicks that once carried messages across continents had been replaced by irregular bursts. Stuttering, uneven, sometimes violent. It was as though an unseen force had inserted itself into the circuit, speaking in pulses no one had learned to interpret. And then came the realization that would unsettle even the most experienced among them. The batteries were no longer necessary. In Boston, technicians disconnected their power sources entirely, expecting the system to fall silent. Under normal conditions, this would have ended all transmission. The telegraph relied on controlled electrical flow. Without it, the network was inert. But the lines did not go quiet. Instead, they continued to carry current, erratic, unpredictable, but undeniably present. Operators found that by carefully timing their inputs, they could still send messages. Not continuously, not reliably, but in bursts. Signals would travel, pause, then return again, as if governed by some external rhythm. Reports described intervals ranging from 30 to 90 seconds between usable transmissions. A message would pass through clearly, then dissolve into noise, then, unexpectedly, clarity would return. It was not human timing. It was something else. Across the network, similar patterns emerged. Operators who dared to experiment discovered that their systems could function intermittently without any internal power at all. The current was coming from outside the designed architecture, entering the wires from the environment itself. The implications were difficult to grasp. Electricity, as it was understood in 1859, was something generated, controlled, and directed. It flowed from batteries through wires into devices. It obeyed the boundaries imposed upon it. It did not appear spontaneously. It did not surge through systems uninvited. And yet that is exactly what was happening. The Earth itself had become a source of current. Beneath the telegraph lines, beneath the cities and fields and oceans, electrical energy was moving, vast, diffuse, and powerful. It flowed through the ground into the metal wires and across the network, using the infrastructure as a pathway. The system had not simply malfunctioned, it had been overtaken. What the operators were witnessing was the effect of something that would later be understood as geomagnetically induced currents. Flows of electricity generated not by human design, but by the interaction between Earth's magnetic field and an external disturbance. The mechanism, though complex, follows a precise logic. The Earth's magnetic field is not static. It shifts, responds, and under extreme conditions it can change rapidly. When a powerful disturbance from the sun strikes this field, it causes it to fluctuate, compressing, expanding, and reconfiguring in ways that generate electrical fields across the surface of the planet. These changing magnetic fields induce currents in conductive materials, and in 1859 the most extensive conductive network humanity had built was the telegraph system. Long uninterrupted wires stretching across hundreds, sometimes thousands of kilometers, perfect channels for these induced currents to travel. The longer the wire, the greater the potential difference between its ends. The greater the difference, the stronger the current that could be driven through it. It was a system designed for communication, but under these conditions it became something else entirely. A receiver. The currents flowing through the telegraph lines were not random. They were structured, shaped by the dynamics of the magnetic field above and the conductivity of the Earth below. They surged and receded in patterns that reflected a much larger process, one unfolding at a planetary scale. Operators, unaware of the underlying physics, could only respond to what they observed. Some attempted to adapt, learning to work with the pulses rather than against them. They waited for the moments when the current stabilized just enough to carry a signal, then transmitted quickly before the next surge disrupted the line. It was a crude form of synchronization, aligning human intent with a system they did not control. Others abandoned their stations entirely, unwilling to risk further shocks or fires. Because the danger was not theoretical, the currents were strong enough to heat metal, to produce visible sparks, to ignite paper. In some cases, the energy flowing through the wires exceeded what the system had ever been designed to handle. The infrastructure, built with precision and care, was now being pushed beyond its limits by forces it was never meant to encounter. And yet the most profound aspect of the event was not the damage, it was the realization. The telegraph network had been conceived as a closed system, self-contained, governed by human input, predictable in its behavior. But in that moment, it became clear that it was anything but closed. It was connected to the ground beneath it, to the magnetic field surrounding the planet, and ultimately to the activity of the sun itself. The boundaries that had seemed so clear, the separation between Earth and sky, between natural forces and human technology, were dissolving. What the operators were witnessing was not a failure of their machines. It was the exposure of a deeper system, one that had always been present but had never before revealed itself so dramatically. The Earth was not merely a passive platform upon which technology was built. It was an active participant, a conductor in a circuit that extended far beyond the limits of human design, and the telegraph lines stretching across continents had become extensions of that circuit, unintentionally integrated into a process that spanned millions of kilometers. The infrastructure had not failed randomly. It had been overwritten, its function redefined by a larger system that operated according to its own rules, its own rhythms, its own scale. For those who experienced it, the effect was immediate and tangible. Sparks, shocks, fire, the eerie persistence of signals without power. But beneath those observations lay something far more significant. A shift in understanding, the recognition that the forces shaping their world were not confined to the Earth. They extended outward into space, into the dynamics of a star that, until that moment, had been assumed to be distant, stable, and largely irrelevant to the mechanics of daily life. Now that assumption was beginning to break. Because if invisible currents could enter the ground, travel through wires, and override an entire communication network, then they were not local. They were not accidental. They were being driven by something vast, something external, something powerful enough to reach across the void between worlds and impose its influence on everything it touched. And the question, once it formed, could not be ignored. If these currents were not generated here, then where exactly were they coming from? To understand what unfolded on Earth, one has to leave the planet behind. The disturbances in the wires, the burning skies, the currents rising from the ground, none of it began here. It began 150 million kilometers away on a surface so vast that over 1 million Earths could fit inside it, and so violent that even its quietest moments conceal forces beyond human scale. The sun appears calm when viewed from Earth, a steady disk of light, unchanging, reliable. For most of human history, it has been treated as a constant, a backdrop to existence rather than an active participant in it. But the surface of the sun is not calm. It is a shifting, turbulent ocean of plasma, electrically charged gas, moving in vast convective currents. Temperatures at the surface reach around 5,500 degrees Celsius, while just above it, in the corona, they rise inexplicably into the millions. The entire structure is threaded with magnetic fields, generated by the motion of plasma deep within the solar interior. These magnetic fields do not remain stable. They twist, they stretch, they tangle, and sometimes they break. The dark regions Carrington had been observing that morning, sunspots, were not imperfections in the sun's surface. They were markers of intense magnetic activity. In these regions, the magnetic field rises up from the interior, piercing the surface and looping back down again, creating vast arcs of energy that can span tens of thousands of kilometers. Within these loops, energy builds, not slowly but relentlessly. As the magnetic field becomes more twisted and complex, it stores energy, immense quantities of it like tension wound into a coiled spring. The plasma trapped within these fields follows their shape, moving along invisible lines of force. But the configuration is unstable. It cannot hold indefinitely. At a critical point, the structure collapses. This process is known as magnetic reconnection. Field lines snap, break apart, and reconnect in new configurations. In doing so, they release the energy that had been stored within them, suddenly, violently, and with extraordinary intensity. The result is a solar flare. In a matter of minutes, energy equivalent to billions of atomic bombs is released. Radiation floods outward across the electromagnetic spectrum, X-rays, ultraviolet light, visible light, all emitted in a burst that can outshine the rest of the solar surface in localized regions. This is what Carrington saw: a flash, a rupture, a moment where the sun's surface revealed something far more volatile than anyone had imagined. But the flare itself, as powerful as it is not the most dangerous part. It is only the signal. Because alongside many solar flares, something else is released. Something slower, heavier, and far more consequential: a coronal mass ejection. Unlike the flare, which is primarily a burst of radiation traveling at the speed of light, a coronal mass ejection is physical. It is a vast cloud of plasma, billions of tons of charged particles ripped free from the sun's outer atmosphere and hurled into space. Embedded within this cloud is its own magnetic field carried outward as it expands. The scale is difficult to visualize. A single CME can span millions of kilometers across. Its mass can exceed 1 billion tons, and its speed in extreme cases can reach several million kilometers per hour. At those velocities, the journey from the Sun to Earth, a distance that light covers in just over 8 minutes, can be completed in less than a day. In the case of the event Carrington witnessed, the transit time was approximately 17 hours. That speed alone tells a story. It suggests not just a release of energy, but an alignment of conditions: magnetic orientation, plasma density, velocity, that allowed the ejected material to travel with minimal resistance, maintaining its structure as it crossed the vastness of space, and crucially, it was directed toward Earth. Most solar eruptions disperse harmlessly into space. The Sun emits energy in all directions, and the probability of a direct impact is relatively low. But when a CME is aligned with Earth's position, and when its internal magnetic field is oriented in a way that interacts strongly with Earth's own, the result can be profound. The magnetic field carried by the CME does not simply pass by. It connects. If the orientation is opposite to that of Earth's magnetic field, the two can link through reconnection, allowing energy and particles to flow directly into the magnetosphere. It is not a collision in the conventional sense. It is a merging of systems. Energy is transferred, momentum is exchanged, and the boundary that normally protects the planet begins to weaken. In 1859, this process occurred with exceptional intensity. The CME that followed Carrington's flare was not ordinary. Its speed, its density, and its magnetic configuration combined to produce one of the most powerful geomagnetic disturbances ever recorded. When it reached Earth, it did not glance off the magnetic field. It engaged with it. The magnetosphere compressed under the impact, shrinking on the side facing the Sun. Field lines stretched and reconnected, channeling energy toward the poles and under such extreme conditions far beyond them. The system began to oscillate, generating electric fields across the surface of the planet. This is what drove the currents in the telegraph lines. This is what ignited the skies. This is what transformed Earth temporarily into part of a larger electrical circuit. But at the moment Carrington observed the flare, none of this had yet occurred. The light he saw, the sudden blinding patches of white, was only the first indication that something had changed. The radiation from the flare reached Earth in minutes, affecting the upper atmosphere, altering ionization levels and contributing to the initial disturbances. But the mass, the vast cloud of plasma carrying embedded magnetic fields, was still en route, traveling through space, expanding, maintaining its structure across millions of kilometers, unseen, unstoppable. And as it moved closer, closing the distance between the Sun and Earth, the conditions for something far more disruptive were already falling into place. Because the true power of such an event is not in the flash that marks its beginning. It is in the arrival that follows. The moment when a star, separated from its planet by an expanse so vast it seems untouchable, reaches across that distance and makes contact, not with light alone, but with force. Carrington saw the signal. He recorded the moment. But what he witnessed was only the surface expression of a much larger process, one that had already begun to unfold beyond his view. The real storm, the one capable of reshaping magnetic fields, driving currents through continents, and turning night into something else entirely, was still on its way. 17 hours. That was all the time it took for the Sun to reach across 150 million kilometers of space and touch the Earth. In cosmic terms, it was instantaneous. A violent release of plasma had erupted from the solar surface, accelerated to extraordinary speeds, and now, less than a day later, it arrived. Not as light, which had already passed unnoticed in minutes, but as mass, as structure, as a moving field of charged particles carrying with it the imprint of the sun's magnetic architecture. There was no sound, no visible object streaking across the sky, no impact in the way the human mind instinctively understands it. And yet, the moment it reached Earth, everything began to change. The planet is surrounded by an invisible shield, a magnetic field generated deep within its core, extending outward into space. This magnetosphere is not a static barrier. It breathes, shifts, and flexes under the constant pressure of the solar wind, a steady stream of particles flowing outward from the sun at hundreds of kilometers per second. Under normal conditions, this interaction is stable. The magnetosphere deflects most of the incoming particles, guiding them around the planet, preserving the atmosphere and protecting life below. But this was not a normal condition. The incoming cloud from the sun was denser, faster, and magnetically structured in a way that made it far more dangerous. As it approached, it carried its own magnetic field, compressed, twisted, and aligned in opposition to Earth's own. And when those two fields met, they did not simply collide, they connected. The first effect was compression. On the side of the Earth facing the sun, the magnetosphere was forced inward, squeezed by the sheer momentum of the incoming plasma. What normally extended tens of thousands of kilometers into space was suddenly pushed closer, tightened, reshaped. The boundary that separated Earth from the surrounding environment became thinner, more strained. But compression alone does not explain what followed. The real transformation occurred at the boundaries of these magnetic fields, where opposing directions met and something fundamental began to happen. Magnetic reconnection. Under extreme stress, magnetic field lines, normally stable structures, can break and reconnect in new configurations. When the field carried by the solar plasma encountered Earth's magnetosphere, the opposing orientations created the perfect conditions for this process. Field lines snapped, they reattached, and in doing so, they opened pathways. Energy that had been confined within the solar plasma now had a direct route into Earth's magnetic system. Charged particles flowed along these newly formed connections, accelerating toward the poles, spiraling along field lines, injecting energy deep into the magnetosphere. This was not an impact in the conventional sense. No object struck the ground, no crater formed, no shockwave rippled across the surface. What occurred was more subtle and far more pervasive. The planet was electrically invaded. Energy entered not as a single force, but as a distributed process. It spread through the magnetic field, inducing currents, altering the balance of forces that governed the behavior of charged particles in near-Earth space. The entire system began to respond, not in isolation, but as a whole. The magnetosphere, once a shield, became a conduit. And as it absorbed this energy, it did not simply dissipate it, it transformed it. The incoming particles, guided by magnetic field lines, collided with atoms in the upper atmosphere. Oxygen and nitrogen, excited by these interactions, released photons, producing the brilliant auroras that now stretched far beyond their usual boundaries. What had once been confined to polar regions now spilled across latitudes that had never experienced such displays. But the transformation did not stop in the sky. The changing magnetic field induced electric fields across the surface of the Earth. These fields, in turn, drove currents through the ground, through oceans, through anything capable of conducting electricity. The planet itself became part of the process, responding dynamically to the energy flowing into it. It was not passive, it was active. The Earth was not merely receiving energy from the sun, it was interacting with it, redistributing it, converting it into forms that could manifest across multiple systems simultaneously. In the magnetosphere, energy became motion, charged particles accelerating along invisible khutut. In the atmosphere, energy became light, auroras painting the sky in shifting colors. In the ground, energy became current, flowing through soil and rock, seeking pathways of least resistance. And in human technology, those pathways had already been built. The telegraph lines, stretched across continents, provided ideal channels for these induced currents. Long conductors spanning vast distances allowed the electric fields generated by the shifting magnetosphere to drive currents directly into human infrastructure. The result was the chaos unfolding in telegraph offices around the world. But that chaos was only a symptom. The underlying process was far larger, because once the magnetosphere had been opened, once reconnection had allowed energy to flow freely into the system, the dynamics of the entire environment changed. The system did not stabilize immediately. It oscillated, it surged, it released energy in bursts, each one feeding into the currents below, into the lights above, into the instruments that struggled to measure it. This was not a single moment, it was an ongoing interaction. The sun had not simply sent a pulse of energy, it had initiated a process that unfolded over hours, even days, as the magnetosphere adjusted, reconfigured, and gradually returned toward equilibrium. But during that time, the Earth was no longer isolated. It was part of a larger circuit, connected directly to the activity of its star. And within that connection lay a realization that would take decades to fully understand. The forces shaping the planet were not confined to its surface, nor even to its atmosphere. They extended outward, into space, into the dynamics of a star whose behavior could reach across vast distances and alter conditions on Earth in ways that were both subtle and profound. What Carrington had witnessed was the beginning of that process. What followed, this invisible interaction between plasma and magnetic field, between star and planet, was its true expression. Because the Earth did not simply endure the arrival of that solar storm. It responded to it. It absorbed it. It redistributed it across systems both natural and artificial. And in doing so, it revealed something that had always been true but had never been experienced so clearly. The planet did not just receive energy from the sun. It became part of the system through which that energy flowed. The violence of the event was never visible in a single place. There was no central point of destruction, no epicenter in the traditional sense. Instead, what unfolded was distributed across continents, an electrical phenomenon so vast that it could only be understood by examining its effects on systems stretched across the surface of the planet. At the heart of it lay a simple principle of physics that, under normal conditions, remains hidden from human awareness. When a magnetic field changes rapidly in time, it generates an electric field. This is not an exception. It is not a rare condition. It is a fundamental law of nature. And during the solar disturbance of 1859, Earth's magnetic field was changing at extraordinary speed and scale. As the compressed magnetosphere oscillated under the pressure of the incoming solar plasma, the field lines did not simply bend and settle. They moved dynamically, shifting position across vast regions of space. Each change propagated an electric response through the environment, inducing currents wherever conductive pathways existed. On a planet covered in rock, ocean, and atmosphere, those pathways are everywhere. But in 1859, the most efficient pathways were not natural. They were engineered. The telegraph network had been built to span distance, not to interact with planetary-scale electromagnetic forces. Thousands of kilometers of copper wire stretched between cities, often elevated on poles, sometimes buried, sometimes exposed to the open air. These lines were designed to carry controlled currents generated locally by batteries. They were never designed to respond to the planet itself. But that is exactly what happened. Each long wire acted as an antenna, not in the modern sense of receiving radio signals, but in the more fundamental electromagnetic sense. A conductor immersed in a changing magnetic field will develop a voltage along its length. The longer the conductor, the greater the difference in potential between its ends. In practical terms, this meant that a telegraph line running hundreds or thousands of kilometers was effectively experiencing two different electrical environments simultaneously. At one end, the magnetic conditions were slightly different from the other. That difference was converted into electrical pressure, a voltage that forced current to flow through the wire. And because the magnetic disturbance was global, these effects were not isolated, they were synchronized. Across North America, Europe, and beyond, telegraph systems began to behave as if they were all connected to a single invisible power source. Not because they were linked to one another, but because they were all embedded in the same changing magnetic environment. The Earth itself had become the generator, but the wires were not the only conduits. Beneath them, currents were flowing through the ground. These are known as geomagnetically induced currents, flows of electricity driven through the Earth's surface and subsurface layers by rapidly changing magnetic fields above. Unlike currents in wires, ground currents do not follow a single defined path. They spread, diffuse, and concentrate depending on the conductivity of the materials they encounter. Rock, soil, and seawater all respond differently, but all can carry current under sufficient force. During the 1859 event, the strength of these induced fields was enough to drive measurable currents through the Earth itself. In some cases, these ground currents entered telegraph systems through grounding points, merging with the currents flowing in the wires above. The distinction between line and earth began to blur. Electricity was no longer confined to engineered circuits. It was circulating through the planet. This is where the system began to reveal a deeper truth. The vulnerability was not simply a matter of faulty equipment or insufficient shielding. It was structural. It was scale-dependent. Long conductors are more sensitive to changing magnetic fields because they integrate the effect of that change over distance. A short wire might experience a small localized voltage. A long wire experiences the cumulative difference across hundreds or thousands of kilometers. This is why the telegraph network was so severely affected. It was not fragile in a mechanical sense. It was vast in a way that made it inherently responsive to planetary-scale electromagnetic disturbances. And this leads to the critical insight that would only be fully appreciated much later. The larger a system becomes, the more energy it can absorb from external fields. In a small system, disturbances are localized. Energy is limited by the boundaries of the structure. But as a system expands, geographically, electrically, or technologically, it begins to intersect with larger and larger portions of the environment. It becomes exposed to more variations in field strength, more gradients, more potential differences. In effect, scale becomes coupling. The telegraph network did not just span continents. It coupled those continents to the dynamics of the Earth's magnetic field, and the Earth's magnetic field in turn was being driven by something far more powerful than anything within human experience: the sun. This is why the effects of the storm were so widespread. It was not because energy was targeted at specific locations, but because the entire planetary system was being driven simultaneously. Wherever there was a conductive pathway, current was induced. Wherever there was a long enough conductor, voltage accumulated. Wherever there was a closed circuit, energy flowed. The planet had become an integrated electrical environment, and human technology, for the first time in history, was embedded within it. Operators in telegraph stations were not simply witnessing equipment failure, they were observing the interaction between two systems operating at vastly different scales. A human-engineered network designed for controlled communication, and a planetary electromagnetic system responding to solar forcing. At times, the two systems interfered destructively, producing sparks, fires, and disruptions. At other times, they temporarily aligned, allowing messages to pass without conventional power sources. But in both cases, the outcome was determined not by human control but by external conditions imposed on the entire system simultaneously. The illusion of isolation had been broken. What appeared to be independent infrastructure was in reality embedded within a much larger field of influence. And that field was not static. It was dynamic, responsive, and capable of change on a scale that dwarfed anything occurring on Earth's surface. The telegraph network was simply the first system large enough, long enough, and conductive enough to reveal this interaction in a visible way. It acted as a sensor, not by design but by consequence, registering fluctuations in the planet's electromagnetic environment. But even as this realization began to emerge, the true scale of the issue remained obscured. Because the telegraph system, large as it was in 1859, represented only the earliest stage of technological connectivity. It was a sparse network compared to what would eventually follow. Its conductors were few, its reach limited, its dependence on electrical continuity still partial. It was large enough to be affected, but not large enough to represent the full potential of a connected planet. And that is where the deeper implication lies. Because if a relatively simple network of wires could be driven into chaos by a solar disturbance of this magnitude, then what happens when the network becomes global? When every continent is connected not by isolated lines but by continuous electrical infrastructure, when satellites extend the system beyond the atmosphere itself, when timing, navigation, communication, finance, and power distribution all rely on synchronized electromagnetic stability. In 1859, the system was small, localized, fragmented, incomplete. But the physics that affected it did not remain in the past. They scale, they persist, and they remain active today. The telegraph wires have long since been replaced, but the circuit they revealed has only grown larger. And what was once a disturbance confined to a few fragile lines across continents now has the potential to interact with something far more extensive, something that now spans the entire planet. Before we proceed, do you understand the physics here? If not, feel free to ask questions or share your thoughts in the comments. In 1859, the network was thin. A handful of copper lines stretched across continents powered by local batteries limited in reach and scale. When the sun struck, it exposed that network's vulnerability, but it was still, in absolute terms, a primitive system. It could fail, burn, distort, and recover. The modern world does not have that luxury. What exists today is not a network of wires. It is a continuous interlinked electrical organism, an integrated grid that spans nations, continents, and, through satellites, the space above Earth itself. It is not just a communication system. It is the nervous system of civilization, and it is far more sensitive than anything that came before it. At the heart of this system are components designed for stability under carefully controlled conditions. Among the most critical are high-voltage transformers, massive devices that step voltage up and down as electricity moves across long distances. They regulate flow between generation plants, transmission lines, and distribution networks. Without them, power cannot move efficiently across modern grids. But these transformers have a fundamental vulnerability. They are not designed for uncontrolled geomagnetically induced currents. During a solar storm, the same mechanism that drove currents through telegraph lines in 1859 operates on a vastly larger infrastructure. Rapid changes in Earth's magnetic field induce quasi-direct currents in long conductors, modern equivalents of those copper wires, but now expanded into national and continental grids. Transmission lines stretching hundreds or thousands of kilometers act as enormous antennas, just as they did in the 19th century. But instead of feeding simple telegraph systems, they now feed transformers designed for alternating current, not sustained direct current-like influxes. This distinction is critical. Transformers rely on magnetic cores that are engineered to operate within specific limits of flux. Under normal conditions, the alternating current flowing through them produces predictable magnetic oscillations. But when a geomagnetically induced current enters the system, it effectively biases the core with a steady offset. The result is saturation. When a transformer core becomes saturated, it loses its ability to regulate magnetic flux properly. The system begins to draw excessive current, producing heat far beyond design limits. Protective mechanisms may activate, but in extreme cases, they are not sufficient to prevent failure. Once a transformer fails, it does not simply reset. High-voltage transformers are among the most complex and specialized pieces of electrical infrastructure ever built. They are custom-engineered, often weighing hundreds of tons, requiring months or even years to manufacture and transport. There is no global stockpile of replacements ready for immediate deployment. Each unit is built for a specific location within a specific grid configuration. This creates a structural vulnerability that did not exist in 1859. Because while telegraph systems could be repaired with relative speed, modern grids depend on components that cannot be rapidly replaced at scale. And the risk is not theoretical. Scientific agencies have studied these phenomena in detail. Analyses conducted by organizations such as NASA and the U.S. National Academy of Sciences have modeled extreme space weather scenarios. Their findings converge on a consistent conclusion. A Carrington-class event striking today's infrastructure would not be a localized disruption. It would be a systemic failure. Transformers across multiple continents could be driven into saturation simultaneously. Protective relays might trigger widespread shutdowns, attempting to prevent damage but effectively disconnecting entire regions from the grid. In worst-case scenarios, physical damage to key substations could cascade outward, fragmenting interconnected systems into isolated, non-functional islands. Power is not just generation, it is synchronization, and synchronization depends on stability across vast distances. The modern grid is no longer a simple network of supply and demand. It is a tightly coupled system where frequency, phase, and load must remain balanced continuously. Even small disturbances are managed through automated control systems that assume external conditions remain within known physical limits. A solar storm of sufficient magnitude violates those assumptions. At the same time, the vulnerability extends beyond terrestrial power systems. Above the atmosphere, satellites form another layer of dependence. They regulate communication, navigation, weather forecasting, financial timing, and military coordination. These systems operate in regions where the magnetosphere normally provides partial shielding. But during extreme events, that protection weakens and distorts. Energetic particles can penetrate satellite electronics, causing bit flips, system errors, and in severe cases, permanent damage. Atmospheric expansion caused by solar heating can increase drag on low-orbit satellites, altering trajectories and reducing orbital stability. What appears from the ground as a silent sky is, in reality, an active electromagnetic environment, one that modern technology is deeply embedded within. The critical difference between 1859 and today is not just scale, it is integration. In the 19th century, disruption affected communication. In the modern world, it affects communication, power distribution, financial systems, navigation, logistics, and emergency response simultaneously. Each system depends on the others. Each one assumes the stability of the rest. This interdependence creates a condition where failure is not isolated, it is cascading. If a transformer fails, it affects regional power. If power fails, communication systems degrade. If communication degrades, coordination collapses. If coordination collapses, recovery slows. Each layer feeds into the next. The system does not simply break, it unravels. And this is where the historical comparison becomes essential. The Carrington Event did not occur in a modern world. It struck a system that was small, fragmented, and largely independent of global electrical infrastructure. Even then, it produced fires in telegraph stations, disrupted communications across continents, and induced currents strong enough to operate equipment without power sources. Now imagine that same physical mechanism applied to a system that is no longer fragmented, a system that is continuous, a system that spans entire continents, connects oceans through undersea cables, extends into orbit through satellites, and depends on precise electromagnetic stability to function at every level. The question is no longer whether the same physical processes can occur. They can. They do. Solar storms continue to strike Earth regularly. Most are weak, some are moderate, and a few approach the scale of historical extremes. The sun has not changed its behavior. The physics has not changed. Only the complexity of the system it interacts with has grown. And with that complexity comes a new kind of vulnerability. Because the more interconnected the system becomes, the more points it has through which external energy can enter. The more dependent it is on continuous electrical stability, the more sensitive it becomes to disturbances in that stability. A system that once required a massive solar event to reveal its weakness may now require only a fraction of that intensity to cause widespread disruption. This is not speculation in the abstract sense. It is a direct consequence of scale, connectivity, and dependence on electromagnetic infrastructure, which leads to a difficult realization. The same physical phenomenon that once caused telegraph fires and auroras visible at the equator still exists. The same magnetic interactions still occur. The same solar processes still drive energy toward Earth. But now the system receiving that energy is no longer small enough to absorb it without consequence. It is global, and that raises a question that cannot be avoided. If a 19th century system, limited, sparse, and primitive, was already pushed to the edge of failure by a single solar event, what happens when the system is no longer local at all? What happens when it becomes the entire planet? Let's stimulate a modern Carrington scenario to understand it in detail. It does not begin with impact. There is no explosion, no visible rupture in the sky, no sound that announces the beginning of collapse. Instead, it begins with something far more unsettling. A fluctuation. At first, it is indistinguishable from routine instability. A minor voltage irregularity recorded by monitoring stations, a transient spike in current along high-voltage transmission lines. Automated systems respond as they are designed to, correcting, compensating, stabilizing. But the disturbance does not behave like a local fault. It spreads. Across continents, substations begin to register similar anomalies. Protective relays detect abnormal flows of current and initiate shutdown procedures to prevent damage. In some regions, this works as intended. In others, the systems react too late. The first transformers begin to fail, not in isolation, but in clusters. This is the moment the system transitions from disturbance to cascade. Modern electrical grids are not independent. They are deeply interconnected, synchronized across vast regions to maintain frequency stability. Power generated in one location is distributed across hundreds or thousands of kilometers, balancing demand dynamically in real time. This interdependence is a strength under normal conditions. Under extreme external forcing, it becomes a pathway for failure. As geomagnetically induced currents begin to enter the system, they do not remain confined to a single point of entry. Transmission lines spanning long distances act as conduits, drawing in electrical energy driven by changes in Earth's magnetic field. That energy flows into substations, into transformers, into control systems designed for a very different kind of current behavior. The response is immediate, but not coordinated. Some regions shut down preemptively. Others continue operating as long as possible, unaware that instability is already propagating through the network. Frequency deviations begin to appear across interconnected grids. Small discrepancies in timing, fractions of a second, start to accumulate. And in a synchronized system, timing is everything. When one segment of the grid falls out of alignment, protective systems isolate it. But isolation does not eliminate the disturbance. It redirects it. Load is redistributed to neighboring regions which are already under stress from the same external forcing. Those regions in turn become overloaded. The result is cascading failure, a domino effect not of physical structures but of synchronization loss. Within hours, entire sections of continental grids begin to fragment. Power plants disconnect to protect their equipment. Transmission corridors go dark. Urban centers experience rolling blackouts that quickly become total outages. The scale is not localized, it is systemic. Cities that rely on continuous power for water distribution, transportation systems, communication networks, and emergency services begin to lose those functions simultaneously. Subways halt mid-transit. Traffic systems fail, leading to immediate congestion in dense urban environments. Hospitals switch to backup generators, but fuel supply chains are already destabilizing as logistics networks lose coordination. At the same time, satellite systems begin to degrade. Navigation signals become unreliable. Communication relays experience interference. Timing systems that underpin financial networks drift out of synchronization. Transactions stall, markets freeze. Data centers begin controlled shutdowns to prevent hardware damage from unstable power inputs. The modern world does not simply experience a blackout, it experiences fragmentation. Each system depends on others that are also failing. Power supports communication. Communication supports logistics. Logistics supports fuel delivery. Fuel supports power recovery. As each link weakens, the entire chain begins to unravel. Within the first 24 hours, economic models estimate damages reaching between $1 and $2 trillion. Not from a single catastrophic event in one location, but from simultaneous systemic disruption across multiple critical infrastructures. But the numbers do not capture the lived reality, because what is being lost is not just energy, it is coordination. In the absence of electrical stability, the systems that define modern life lose coherence. Information slows or becomes unreliable. Decisions that depend on real-time data become uncertain. Emergency responses are delayed not by lack of effort, but by lack of communication. Even partial restoration becomes difficult, because repair itself depends on the same infrastructure that has failed. Replacement transformers cannot be delivered if transport networks are disrupted. Grid operators cannot coordinate recovery if communication links are unstable. Every attempt to rebuild is constrained by the absence of the very system being rebuilt. And beneath all of this, the physical driver remains unchanged. The sun continues to emit energy. The magnetosphere continues to respond. Induced currents continue to flow through the ground and infrastructure. The Earth, for a time, remains in a state of electromagnetic agitation, absorbing, redistributing, and reacting to the external forcing imposed upon it. From the surface, however, the experience is total disruption. Lights that once defined the rhythm of human activity, cities glowing at night, infrastructure operating continuously, networks transmitting without interruption, are gone. Not flickering, not dimming, gone. Entire regions fall silent, not in sound, but in signal. The invisible structure that once connected systems across vast distances is no longer functioning. In its absence, localized systems attempt to operate independently, but without synchronization, efficiency collapses. The modern world was not designed for isolation, it was designed for integration. This is what makes the failure so profound. It is not a breakdown of individual components. It is the loss of the relationships between them. The invisible coordination that allowed millions of processes to function simultaneously without direct human oversight disappears. And with it, the assumption of stability. In cities, the absence of light is only the beginning. Water pressure drops as pumping stations lose power. Food supply chains stall as refrigeration and transport systems fail. Financial systems freeze as data centers lose synchronization. Emergency services operate under increasing strain as communication becomes fragmented and unreliable. None of these failures occur in sequence. They occur together because they are all connected. And that connection is electrical. The same physical principle that once caused telegraph wires to spark in 1859 now operates across an incomparably larger system. Long conductors still respond to changing magnetic fields. Induced currents still flow through infrastructure. The physics has not changed, only the scale has, and scale determines consequence. As night falls again over the affected regions, there is no return to normal illumination. The darkness is not temporary, it is structural, but the absence of a functioning system to distribute it. Above the atmosphere, satellites drift in compromised states. Some systems reboot, others fail entirely. Below, power networks remain unstable, fragmented into isolated pockets, attempting to function independently. The planet is still connected, but the connection is no longer coherent, and in that fragmentation lies the deeper realization. Modern civilization is not defined by individual technologies. It is defined by the continuity between them. When that continuity breaks, what remains is not a weakened version of the same world. It is something fundamentally different. A world in which the invisible architecture that once held everything together has temporarily ceased to function. And the cause of that failure is still above the horizon, still interacting with Earth's magnetic field, still driving currents through systems that were never designed to withstand it. Above the darkness of the planet, the failure does not arrive as silence, it arrives as distortion. Satellites, thousands of them, continue their silent trajectories through low Earth orbit and geostationary space. To the human eye, nothing appears changed. The night sky remains largely the same, faint points of light, mechanical, indifferent, moving in predictable arcs. But inside those systems, something has already begun to break. The first impact is invisible. High-energy particles, accelerated by the solar disturbance, penetrate the outer shielding of satellites. These particles are not physical debris, they are subatomic, protons and electrons moving at extraordinary velocities, capable of passing through materials designed for far less extreme conditions. When they strike microelectronics, they do not destroy them in a single dramatic moment. Instead, they disrupt them at the level of information. A flipped bit in memory, a corrupted instruction, a misread sensor value. One error is insignificant. Systems are designed with redundancy for exactly this reason. But under sustained exposure, errors begin to accumulate across multiple systems simultaneously. Satellites controlling communication networks begin to experience anomalies. Data packets become inconsistent, signal timing drifts, error correction systems engage more frequently, consuming computational capacity that would normally be used for stable operation. Then comes the second layer of stress. Earth's upper atmosphere responds to solar energy input by heating and expanding. This is not heat in the everyday sense, but an increase in particle energy at altitudes where the atmosphere is normally extremely thin. As it expands, the density at orbital altitudes increases. For satellites in low Earth orbit, this change is critical. Even a slight increase in atmospheric density creates drag, subtle resistance that slows orbital velocity. Over time, this causes orbital decay. Satellites begin to lose altitude. their trajectories shift. Systems that rely on precise orbital calculations must constantly adjust to maintain stability. But during a geomagnetic disturbance of this scale, the rate of change is not uniform, it fluctuates. Some regions of orbit experience stronger expansion than others. Some satellites are affected earlier, others later. The result is a loss of predictability across the entire orbital environment. And predictability is the foundation of orbital mechanics. As satellites struggle to maintain position, control systems on the ground begin issuing corrective commands. But these commands depend on communication links that are themselves becoming unstable. Delays increase. Signal degradation worsens. Feedback loops become less reliable. The system begins to lose coherence. Among the most immediately affected networks is GPS. Global Positioning System satellites rely on extremely precise timing signals, synchronized to atomic clocks. Even nanosecond-level discrepancies can produce measurable positional errors on the ground. Under normal conditions, this system is remarkably stable. A distributed constellation of satellites ensures redundancy and accuracy through constant cross-referencing. But during a solar storm, that precision becomes vulnerable. Radiation-induced errors in onboard clocks combined with atmospheric effects on signal propagation introduce inconsistencies. Timing signals drift. Positional data becomes less reliable. Navigation systems on the ground begin to show small but compounding inaccuracies. At first, the errors are negligible. A few meters off course, a slight delay in synchronization. But modern infrastructure does not treat GPS as a convenience. It treats it as a foundational reference system. Financial networks, for example, rely on precise time synchronization to validate transactions across global markets. Even microsecond discrepancies can affect high-frequency trading systems where billions of dollars move based on temporal ordering of events. When satellite timing becomes unstable, these systems begin to desynchronize. Transactions cannot be verified consistently. Systems pause, retry, or enter protective states to avoid corruption. Trading slows, automated systems halt. Data centers begin isolating themselves from external inputs to prevent cascading errors. At the same time, communication satellites experience degradation in signal integrity. Some are temporarily blinded by radiation interference. Others begin to operate in degraded modes, reducing bandwidth to maintain stability. Entire communication channels become intermittent or unreliable. The effect on Earth is not immediately catastrophic in a visible sense. There are no falling objects from the sky. No visible destruction in orbit. Instead, what occurs is a progressive loss of certainty. Systems that depend on satellite data begin to diverge from reality. Navigation becomes less accurate. Communication becomes less consistent. Timing becomes less reliable. And because these systems are deeply embedded in modern infrastructure, their degradation does not remain isolated. It propagates downward. Aircraft navigation systems lose precision. Shipping routes become less efficient. Emergency response coordination becomes slower. Even power grid management, which often relies on synchronized timing signals, begins to experience irregularities. What exists in orbit is no longer a stable support system, it is a fluctuating variable. A layer of infrastructure under stress, transmitting that stress downward through every system that depends on it. And this is where the deeper dependency becomes visible. Modern civilization does not simply use satellites, it is built around them. They are not auxiliary systems, they are foundational. They provide timing, positioning, communication, weather monitoring, and synchronization across nearly every sector of global infrastructure. And yet they are invisible in daily life. Most people never see them, never think about them, never consider the delicate balance of radiation shielding, orbital mechanics, and electromagnetic stability required for their continuous operation. They exist above perception, assumed to be stable because they are normally silent. But silence is not stability. It is dependency without awareness. As the solar disturbance continues, the satellite layer becomes increasingly unstable. Some systems recover temporarily as the magnetic environment fluctuates. Others degrade further, accumulating errors that eventually force them into safe modes or partial shutdowns. The orbital environment itself becomes dynamic, not chaotic in appearance but unstable in structure. A system designed for predictability is now operating under conditions of sustained external forcing. And beneath it all, the source remains unchanged. The sun continues to emit charged particles. The magnetosphere continues to respond. Energy continues to flow through the coupled system of space, atmosphere, and ground. But the human layer of technology, built on assumptions of stability in that environment, is no longer operating within expected boundaries. Each layer of infrastructure depends on the stability of the others. Satellites depend on orbital predictability. Ground systems depend on satellite synchronization. Communication networks depend on both. Financial systems depend on all of them simultaneously. When one layer begins to fail, the effects do not remain isolated. They cascade downward, not as physical collapse, but as loss of coordination. And coordination is what modern civilization is built upon. As orbital systems continue to degrade, a realization begins to emerge across technical monitoring centers and observatories tracking space weather in real time. The failure is not localized to orbit. It is systemic. Orbit is not separate from Earth. It is part of the same coupled environment, a region where solar energy, magnetic fields, atmospheric dynamics, and human technology intersect. And when that region becomes unstable, the effects do not remain above. They propagate downward, into systems that were never designed to operate without it. Because when the sky stops functioning as a stable layer of infrastructure, the systems beneath it begin to inherit that instability. In financial systems spread across the globe, transactions depend on synchronization down to fractions of a second. Every trade, every settlement, every transfer is ordered by timestamps generated by highly precise atomic clocks. These clocks are constantly corrected, constantly compared, constantly aligned through satellite-based timing systems that ensure global consistency. Under normal conditions, this creates an illusion of absolute temporal coherence. From New York to London to Tokyo, markets move in a synchronized rhythm. Millions of transactions occur, all anchored to a shared temporal framework. But when the satellite layer begins to degrade, that framework starts to fracture. At first, the discrepancies are microscopic, nanoseconds, barely measurable differences between systems that should, in theory, be identical. But financial systems are not tolerant of ambiguity. They are built on exact ordering. If two events cannot be precisely placed in sequence, uncertainty emerges. And uncertainty in financial systems is not neutral. It is destabilizing. As solar-induced disturbances continue to affect satellite timing signals, those nanosecond discrepancies expand. Systems in different regions begin to disagree on the order of events. A transaction that appears valid in one node is rejected in another. Automated systems pause to reconcile conflicting data, but reconciliation requires stable reference points that are no longer fully reliable. The global financial network begins to slow, not collapse, not yet. But hesitation spreads through a system that was never designed to hesitate. At the same time, in the atmosphere below, aviation systems begin to experience a different kind of failure. Aircraft rely on multiple layers of navigation, inertial systems, ground-based radio beacons, and increasingly, satellite positioning. When GPS accuracy degrades, pilots and autonomous systems must fall back on redundant systems. But redundancy assumes partial failure, not systemic distortion. As satellite signals fluctuate, positional data becomes inconsistent. An aircraft may appear slightly off course, then correct itself, then drift again. These oscillations are small, but in aviation, small deviations matter. Flight paths are calculated with precision not just for efficiency, but for safety and separation. Air traffic control systems, already strained by communication instability, begin to lose confidence in automated tracking. Manual verification increases workload dramatically. Controllers attempt to cross-reference multiple systems, but those systems no longer agree perfectly with each other. Aviation does not fail all at once. It becomes uncertain. And in systems that depend on certainty to maintain safety margins, uncertainty itself becomes a form of pressure. Meanwhile, beneath both finance and aviation, another layer begins to degrade. The Internet. Not the visible interface of websites and applications, but the underlying infrastructure that holds it together. The Internet depends on synchronized routing, timing protocols, and distributed systems that assume stable communication paths. Data centers exchange information continuously, balancing loads, replicating data, maintaining redundancy across continents. This architecture is resilient, but only within expected environmental conditions. As geomagnetic disturbances continue, fiber optic networks themselves are largely unaffected physically, but the systems that synchronize them are not. Timing servers begin to drift. Packet routing decisions become inconsistent. Latency increases unpredictably as network nodes attempt to compensate for unreliable timing signals. Some data centers isolate themselves preemptively, entering protective modes to prevent corruption. Others continue operating, but with degraded efficiency. The result is not a clean disconnection, it is fragmentation. Sections of the Internet begin to behave as semi-independent systems. Data flows, but unevenly. Some routes remain stable while others degrade. Services that depend on real-time synchronization, cloud computing, global databases, distributed applications, begin to fail in subtle, cascading ways. Users experience delays, outages, inconsistencies. But beneath that experience is a deeper structural problem. The systems that coordinate global information are losing a shared sense of time. And time in modern infrastructure is not abstract. It is operational. Every distributed system relies on synchronized clocks. Without them, it becomes impossible to determine the order of events across different locations. Without order, consistency breaks. Without consistency, systems cannot agree on what is true at any given moment. What emerges is not just technical failure, it is temporal divergence. Different parts of the world begin to operate on slightly different versions of time. Not in the philosophical sense, but in the literal engineered sense of clock synchronization drifting apart under external disturbance. This is where the most profound consequence begins to emerge. Modern civilization is not only built on energy, it is built on coordination. Coordination requires timing. Timing requires synchronization. Synchronization requires stable reference systems that span the entire planet and extend into orbit. When those reference systems begin to fail, the structure built upon them does not simply slow down. It loses coherence. Factories that rely on synchronized supply chains begin to stall. Logistics networks cannot accurately predict arrivals or departures. Communication systems begin to deliver information out of order. Even emergency services, which depend on coordinated response systems, encounter delays caused not by lack of resources, but by lack of reliable timing. The world does not stop functioning. It stops aligning. And alignment is what allows complexity to exist at scale. Without it, systems revert to local behavior. Each region, each network, each infrastructure cluster begins to operate based on its own degraded reference frame. The global system fragments into semi-independent zones, each attempting to maintain internal stability without reliable connection to the rest. This is not collapse in the dramatic sense. It is disintegration of synchrony, the loss of a shared temporal framework. In scientific terms, time itself has not stopped. Atomic clocks still oscillate. Physical processes still occur at the same fundamental rates. But the ability to distribute and maintain a unified temporal reference across a global system has been compromised. And that distinction is critical, because civilization does not require absolute time. It requires shared time, a common framework within which events can be ordered, coordinated, and understood across distance. When that framework begins to fracture, the consequences are not immediately visible as destruction. They appear first as confusion, then inefficiency, then systemic hesitation, then fragmentation. At ground level, this manifests as delays, inconsistencies, and partial failures across multiple sectors simultaneously. No single system is entirely broken, but no system is fully reliable either. And as this state deepens, a realization begins to surface across technical and scientific monitoring centers. The crisis is not localized to power, or satellites, or communication, or finance. It is the synchronization layer itself, the invisible structure that allows all these systems to function as one coherent whole is destabilizing. And without it, complexity cannot be maintained. Because complexity is not just built from components. It is built from coordination between components. As the solar disturbance continues to interact with Earth's magnetic field, inducing currents, disrupting satellites, and degrading timing systems, that coordination continues to erode until what remains is no longer a unified civilization operating in real time, but a collection of systems drifting out of alignment with one another, each still functioning, but no longer together. And that leads to the question that now begins to surface, not as speculation, but as observation of unfolding reality. What happens when a civilization loses not just power, but the ability to stay synchronized with itself? The present crisis does not exist in isolation. It is not a singular anomaly in an otherwise stable history of the Sun. It is part of a pattern, one that stretches across centuries, recorded not in continuous observation but in fragments, telegraph logs, geomagnetic records, auroral descriptions, and the sudden failures of electrical systems that should not have failed at all. To understand what is unfolding, the timeline must widen. Far beyond 1859, far beyond modern infrastructure, back into earlier disturbances that were not understood at the time but now reveal a deeper structure in solar behavior. In 1770, long before electrical grids existed, observers across Asia and Europe recorded something extraordinary. Auroras stretched across latitudes far lower than normal, visible in regions where such phenomena were unknown. Historical records from Japan describe luminous skies persisting for multiple nights, so intense that people mistook them for fires on the horizon. Chinese imperial archives noted unusual atmospheric brightness and magnetic anomalies recorded by early instruments. At the time, there was no framework to explain it, no concept of solar wind, no understanding of magnetic reconnection, no awareness that the Sun could eject vast clouds of charged plasma capable of interacting with Earth's magnetic field. But the signatures were there. A disturbance large enough to extend auroral activity deep into mid-latitudes, a geomagnetic event sustained over multiple days, a solar-driven interaction with Earth's atmosphere and magnetic field, recorded only as unusual light in the sky. It was not understood as a system. It was recorded as an omen. More than a century later, as electrical technology began to spread across the globe, another pattern emerged. In 1921, a powerful geomagnetic storm struck Earth with little warning. Telegraph and early radio systems were disrupted across continents. In New York, a rail switching station caught fire when electrical currents induced by the storm overloaded its systems. Communication networks experienced widespread failure. Operators reported erratic behavior in long-distance circuits similar in nature to those observed in 1859, though in a more technologically advanced context. The infrastructure had evolved, the physics had not. The same mechanism, rapid changes in Earth's magnetic field inducing currents in long conductors, was now acting on a more complex electrical environment. Telegraph wires had been replaced in part by telephone lines, early power distribution systems, and expanding communication networks. The system was larger and therefore more exposed. Then in 1989, the pattern became unmistakably modern. A geomagnetic storm struck Quebec, collapsing the Hydro-Quebec power grid within minutes. 6 million people lost electricity. Transformers in the transmission network experienced saturation and failure due to geomagnetically induced currents. The cascade propagated through the system faster than operators could respond, forcing a controlled shutdown that still could not prevent widespread outage. Unlike earlier events, this was not a sparse network. It was a modern, interconnected grid, and it still failed. What connects these events? 1770, 1859, 1921, 1989 is not coincidence. It is recurrence, each occurring under conditions of heightened solar activity, each interacting with progressively more complex human systems, each revealing in its own way the same underlying physical reality. The sun is not static, it is dynamic, and its dynamics are capable of influencing Earth on scales that range from atmospheric light displays to planetary-scale electrical disruption. The key to this pattern lies in the behavior of the sun itself. Solar activity is not constant. It follows an approximately 11-year cycle known as the solar cycle, driven by the complex dynamics of the sun's internal magnetic field. During this cycle, magnetic activity rises and falls, producing periods of relative calm and periods of intense surface activity. At the peak of this cycle, solar maximum, sunspots become more frequent. Solar flares increase in intensity and coronal mass ejections become more common. It is during these peaks that Earth is most vulnerable to geomagnetic disturbances. But the cycle itself is not perfectly regular. It is not a simple clock. It is a chaotic dynamical system influenced by internal magnetic processes that are still not fully understood. Solar maxima vary in intensity. Some cycles are weak, others produce extreme events that exceed historical expectations. The distribution of solar storms is not uniform but clustered, irregular, and only partially predictable. This is what makes historical events so important. They are not anomalies, they are data points in a longer pattern of variability. Each major geomagnetic storm recorded in human history represents a moment when solar output aligned in a way that allowed energy to couple efficiently with Earth's magnetic field. The frequency of these events suggests that while extreme storms are rare on human timescales, they are not rare on geological or solar timescales. They recur, sometimes separated by decades, sometimes centuries. But they recur nonetheless. And this is where the deeper implication begins to emerge. Human technological development has progressed through these cycles without experiencing a full-scale extreme event in the modern era of global interdependence. The most severe recorded events occurred when systems were simpler, more localized, less integrated. The 1859 event struck a telegraph network. The 1921 event disrupted early electrical systems. The 1989 event collapsed a regional power grid. Each step forward in technology increased both capability and vulnerability. because each increase in scale expanded the surface area through which solar-driven electromagnetic energy could couple into human infrastructure. And yet, despite these warnings embedded in history, the underlying assumption of stability has remained: that the sun is broadly predictable on human timescales. That extreme events are rare enough to be considered external anomalies rather than recurring system interactions. That infrastructure can be designed without accounting for the full range of solar variability. But the historical record suggests otherwise. The sun does not act randomly. It follows rhythms, complex, nonlinear, and only partially understood. Rhythms that produce cycles of relative calm punctuated by episodes of intense activity. Episodes capable of producing effects that scale from atmospheric illumination to planetary electrical disruption. And the longer the observation window becomes, the more these patterns emerge. Not as isolated disasters, but as expressions of an underlying solar behavior that has been present throughout recorded history. In the current moment, as modern infrastructure struggles under the strain of geomagnetic disturbance, this realization becomes more than academic. It becomes operational. Because understanding that these events recur means understanding that the current crisis is not an exception. It is an instance of a repeating physical process interacting with a system that has grown increasingly sensitive to it. The difference now is not the sun. It is Earth's dependence on systems that respond directly to solar variability at every level, from satellites in orbit to transformers on the ground to timing systems that synchronize global activity. Each historical event was smaller in technological consequence than the last, not because the sun was weaker, but because the human system it interacted with was smaller. That relationship has now inverted. The system is larger than ever before, and therefore more exposed than at any point in recorded history. As monitoring stations track the continuing solar activity, and as geomagnetic indices fluctuate in response to incoming plasma streams, a pattern begins to emerge, not just in data, but in understanding. The sun is not a random source of disruption. It is a cyclical driver of space weather. And Earth is not merely a passive recipient. It is a system embedded within that cycle, responding to variations in solar output across multiple timescales, which leads to the unsettling conclusion forming across scientific communities tracking these events in real time. If these storms are cyclical, if they have occurred before modern technology, if they continue to occur with measurable regularity, then the question is not whether they will happen again, but how often and how intense the next cycle will become when it arrives. Risk, in the language of science, is never abstract. It is quantified, modeled, bounded by probability distributions derived from historical data, simulation, and physical constraints. And when it comes to extreme solar events, modern space weather research has converged on a conclusion that is as precise as it is unsettling. A Carrington-class event is not hypothetical. It is expected. Estimates derived from solar observation records, ice core data, and statistical modeling of geomagnetic storms suggest that events of this magnitude occur on the order of once every several centuries. When translated into probability terms, the figure often cited in scientific literature is approximately a 10 to 12% chance per century. Not negligible, not rare in the intuitive human sense. A recurring risk embedded in the timescale of civilizations. But probability alone does not capture the deeper implication, because probability assumes awareness of all relevant occurrences. And in the case of solar activity, that assumption is incomplete. The historical record is fragmented, especially before the advent of modern instrumentation. Even in the satellite era, the observational window is short relative to the full variability of the sun, which means that what is known is only part of what has happened, and even less of what could happen. Within the last few decades, scientists have identified multiple near-miss events, solar storms of significant magnitude that did not strike Earth directly but passed through or near its orbital path, producing measurable disturbances in spacecraft and space weather systems. In the case of solar activity, humanity has developed a form of awareness that is often mistaken for control. Space-based observatories, most prominently the GOES series, operated in geostationary orbit, continuously monitor the sun in multiple wavelengths. They track solar flares, measure coronal mass ejections, and provide early warning of incoming geomagnetic disturbances. These systems are highly advanced. They can detect eruptions as they occur. They can model trajectory. They can estimate arrival times with increasing precision, sometimes down to hours. But there is a critical limitation embedded in this capability. Detection is not prevention. The physical processes that govern solar storms occur at a scale and energy level that is entirely beyond human intervention. A coronal mass ejection is not a signal that can be intercepted. It is not a system that can be redirected. It is a mass of plasma, carrying its own magnetic field released from the sun's corona and propelled through space by forces that dwarf all human technological capacity combined. Once initiated, its trajectory is governed by solar physics and interplanetary magnetic fields. Earth may or may not lie in its path, but nothing on Earth can alter that path. The most that can be done is preparation, and preparation in this context is constrained by infrastructure that was never designed with absolute solar extremes in mind. Power grids can be partially protected. Operators can redistribute load, isolate vulnerable regions, and temporarily shut down key components to reduce exposure to geomagnetically induced currents. Some transformers are designed with higher tolerance thresholds. Some regions have implemented improved grounding strategies to dissipate induced currents more safely. But these measures are not uniform across the globe, and they are not designed for worst-case alignment scenarios. Satellite systems can be placed into safe modes. Non-essential operations can be paused. Sensitive instruments can be powered down temporarily to reduce radiation damage. Redundant systems can be activated to maintain partial functionality. Yet satellites remain exposed environments. They operate within regions of space where shielding is limited and where high-energy particles can still penetrate electronics, degrade materials, and disrupt onboard systems. Even with protective protocols, they remain vulnerable to extreme solar events. Early warning systems, while sophisticated, operate within a narrow window defined by the speed of solar ejecta. Depending on the nature of the eruption, Earth may receive anywhere from a few hours to a day or more of advance notice after detection at the sun. That window is significant for mitigation, but insufficient for structural change. There is no time to redesign infrastructure, no time to reinforce systems at planetary scale, no time to alter the fundamental architecture of dependence. This is the central tension within modern space weather preparedness. Awareness has increased dramatically, modeling has improved, observational capability has expanded into continuous multi-layered monitoring of solar activity. Yet vulnerability remains fundamentally tied to the scale and integration of human systems. Because the same complexity that allows global civilization to function also ensures that disturbances propagate widely once they enter the system. This creates a paradox that cannot be resolved through engineering alone. We can see the incoming disturbance. We can estimate its arrival. We can model its potential effects. But we cannot stop it. This distinction is often obscured in public perception. The presence of satellites, forecasts, and monitoring systems creates the impression of control. But these systems operate in a predictive capacity, not an interventionist one. They describe the system, they do not alter it. And this is where the deeper philosophical dimension emerges. Control implies separation. The idea that the observer stands outside the system, able to manipulate variables from a position of detachment. But in the case of solar-terrestrial interaction, there is no separation. Earth is embedded within the sun's influence. The magnetosphere is not a barrier that eliminates interaction, but a dynamic interface through which energy is constantly exchanged. During extreme events, that interface becomes highly active. Energy flows into the system. Currents are induced across the planet. Atmospheric and magnetic structures respond dynamically. Human technology built atop this environment becomes part of the response, whether intended or not. This challenges a fundamental assumption of technological civilization, that systems can be isolated from external cosmic forces through sufficient design. In reality, isolation is partial. The scale of solar processes exceeds the scale of human intervention. The energy released in major solar eruptions is not something that can be matched, redirected, or counterbalanced by terrestrial systems. Even the most advanced infrastructure exists within, not outside, this energy environment, which leads to a necessary recalibration of perspective. Humanity does not operate above the system, it operates within it. This becomes especially clear when examining how different layers of infrastructure respond during geomagnetic disturbances. Power grids react to induced currents. Satellites respond to radiation and orbital changes. Communication systems respond to timing disruptions. Each system behaves according to its own design constraints, yet all are influenced by the same external driver. A change in solar activity does not target a specific system. It modifies the entire electromagnetic environment in which all systems operate. The result is not isolated failure, but correlated stress across multiple domains simultaneously. And because modern infrastructure is highly interdependent, stress in one domain amplifies stress in others. This is not a failure of design. It is a consequence of integration. The more interconnected systems become, the more they behave as a single coupled structure rather than independent components. This is where preparedness encounters its limit, because preparedness assumes that systems can be stabilized individually. But in a fully coupled environment, stabilization requires control over the entire system, including external drivers. And those external drivers, solar magnetic activity, coronal mass ejections, interplanetary plasma dynamics, are not within human control. They are part of a larger physical process operating on a scale that dwarfs terrestrial engineering, which brings the realization into focus. Preparedness reduces risk. It does not eliminate it. It shifts the outcome curve, mitigates damage, and improves recovery. But it does not alter the underlying interaction between solar activity and Earth's magnetic environment. As long as that interaction exists, so does the potential for disruption. And that potential is not static. It fluctuates with the solar cycle. It increases during periods of heightened activity. It spikes during extreme events. It is influenced by variables that are still being actively studied, modeled, and refined. In that sense, the system is not fully understood. It is partially mapped, partially predictable, and continuously observed, but never fully controllable. And this leads to the final layer of realization emerging from all accumulated data, historical events, and modern modeling. Control was never the correct framework. Participation is. Because Earth is not external to solar dynamics, it is embedded within them. Every magnetic fluctuation, every plasma interaction, every burst of solar energy is part of a continuous physical relationship between star and planet. Human civilization exists inside that relationship. Its technologies do not stand apart from it. They respond to it. They are shaped by it, and during extreme conditions, they reveal it. Which means that the boundary between natural system and human system is not absolute. It is overlapping, and in that overlap, vulnerability and dependence are not anomalies. They are structural properties. As monitoring continues and solar activity remains active across the surface of the Sun, the data does not indicate an endpoint, it indicates continuity. A system still in motion, still capable of producing extremes, still interacting with Earth across magnetic and energetic boundaries that no amount of technological development can fully remove. And within that realization, a final understanding begins to form, not of mastery, not of control, but of position. Because the question was never whether humanity governs the system. The question is what it means to exist inside a system that governs itself and everything within it. The Sun is capable of events stronger than 1859 scale eruptions. Modern observations of other Sun-like stars suggest that superflares, events orders of magnitude more energetic than typical solar flares, are physically possible under certain magnetic configurations. While their frequency on our Sun is still being studied, their existence in the broader astrophysical context confirms that the Carrington Event is not the maximum expression of solar behavior. It is a reference point, a known quantity within a larger spectrum of possibility. This reframes the problem entirely. Because civilization has developed not in isolation from solar variability, but during a relatively calm period of solar behavior. The modern technological era has unfolded without experiencing a full-scale extreme solar event under conditions of global interdependence. That absence is not evidence of safety, it is a temporal coincidence. A window of stability within a system that does not guarantee stability. And this is where the philosophical dimension becomes unavoidable. Stability in physical systems is never permanent. It is a state that exists under specific boundary conditions. When those conditions change, stability can shift rapidly into instability. The modern world depends on assumptions that are not absolute. That power grids will remain synchronized, that satellites will remain operational, that timing systems will remain consistent, that communication networks will remain continuous. These assumptions are not wrong. They are conditional, and conditions can be disrupted by external forcing that operates on a scale far beyond human infrastructure. The Sun represents that external forcing, not as an adversary, not as an anomaly, but as a fundamental participant in the same physical system that includes Earth. It is the source of energy that enables life, drives climate, and shapes the magnetic environment of the planet. It is also the source of disturbances capable of reshaping technological systems built upon that environment. Both roles are expressions of the same underlying physics, which means the distinction between beneficial and destructive is not inherent to the Sun itself. It is contextual, dependent on the state of the system receiving its output. In 1859, that system was simple enough to survive the disturbance. In the present era, it is complex enough to be reshaped by it, and complexity does not inherently imply resilience. It often implies sensitivity, because complex systems depend on tight coupling between components. When that coupling is disrupted, the effects propagate rapidly and widely. This is the underlying vulnerability of modern civilization, not fragility in individual components, but interdependence across all components simultaneously. And that interdependence is mediated by electromagnetic stability, which is precisely what solar storms disrupt. So the Carrington Event becomes more than history. It becomes a boundary case. A recorded instance of what happens when solar energy interacts with Earth's magnetic field under conditions that were not yet fully technologically saturated. And it raises a question that cannot be avoided. What happens when the same physical process occurs again, but the system it interacts with is no longer sparse, but global, continuous, and deeply synchronized? The answer is not speculative. It is structural. The more integrated the system, the more pathways exist for disruption. The more dependent it becomes on continuous synchronization, the more sensitive it becomes to temporal and electromagnetic disturbances, and the more it extends into orbit, the more it is exposed to the full range of solar variability. This is the reality that emerges when the Carrington event is placed in its proper context, not as a one-time catastrophe, but as a demonstration of coupling between star and planet. A coupling that has always existed and will always continue, which brings the understanding full circle. The sun is not separate from human existence. It is the condition under which human existence occurs. It is both the source of stability and the source of disruption, depending entirely on the state of the system that receives it. Civilization in this frame is not built outside that relationship, it is built within it. And that leads to the final realization. Humanity did not survive 1859 because it had mastered the system. It survived because the system had not yet reached the level of dependency that would make such an event existential. That difference no longer exists. The next time the sun releases a storm of comparable magnitude or greater, it will interact with a world where every critical system is interconnected, synchronized, and dependent on electromagnetic stability at planetary scale. And in that moment, it will not be a question of whether we understand what is happening. It will be a question of whether understanding arrives in time to matter. Because the next time the sun speaks, we may finally understand how little control we ever had. If this journey through our past helped you understand what it takes to survive, subscribe to Science of Survival. We release new documentaries every week, exploring extinction, adaptation, and the fragile line that keeps humanity alive.